Question 3, playing ball. Oscar loves chasing his ball. Tobin is teasing Oscar by throwing the ball up in the air and catching it. The ball has a mass of 64 grams. Notice this is not SI units, you need to convert it to kilograms. Tobin throws the ball vertically upwards. Its speed when it leaves Tobin's hand is 5 meters per second. Show that the kinetic energy of the ball when it leaves Tobin's hand is 0.80 joules. Okay, so they've given you a bit of a hint here. They've told you the answer. They want you to work it out. You can't use this number in your working out to prove that that is the right answer. So we have the formula, kinetic energy equals a half mass times velocity squared. We know that the mass is 64 divided by 1,000, because 64 grams, we're going to turn it into kilograms, I have to divide it by 1,000, and I'm going to times that by the speed, which is 5.0 squared. So if I grab out my calculator, and I'm going to go 1 ABC2, which means a half, and I'm going to go times, I'm going to use brackets, 64 divided by 1,000, and I'm going to times that by 5 squared, and that's going to give me 0.8, which is what they're looking for, which is great. So that equals 0.80 joules. B, the ball slows down as it rises because there are forces doing work against the ball's motion. State the forces that are acting against the ball's motion. So they are gravity and friction. So gravity is pulling the ball down, so there's a downwards force, a weight force, and the ball is colliding with air molecules, which is creating friction. II, how much work has been done on the ball to bring it to a stop at its highest point? Well, when you look at your formula sheet, you're going to see that work equals force times distance, and you're going to read through here and there's no distance, and you're like, okay, how do I do this? Well, I know that work is equal to the change in energy. Okay, so it's got kinetic energy when it starts off with, and it gains gravitational potential as it goes to the top, and then it comes back down. I can use gravitational potential energy as mass times gravity times height. I know mass, I know gravity, I still don't know height, so that's not going to work for me. But I do know what the kinetic energy was. So it started off up here with 0.80 joules of kinetic energy, and all of that kinetic energy when it started was going upwards, and then the ball stops at the top, and so it's got only EP, and then it begins to come back down, and then once it gets to the same height, it's got all that potential energy is converted to kinetic. And so if we assume energy conservation, then how much work has been done to stop it is just EK at the start. So I'm going to put a little initial, so initially, and so it's 0.80 joules. So it's really a question of, do you understand what work done means? And because it does ask you to explain your answer, we need to give some sort of explanation. So at the bottom, all the energy is in the form of kinetic energy. At the top, it stops, so it doesn't have any kinetic energy anymore. So all of the energy has been converted into gravitational potential energy, assuming no energy losses or unforeseen energy transfers into heat and sound. So the kinetic energy, EK at the start, must equal the potential energy at the end. The work done is a change in this energy, which is 0.80 joules, i.e. the ball started with 0.80 joules of kinetic energy. At the top, it has 0 joules of kinetic energy. That energy change is 0.80 joules, which is the work done on the ball. C, Tobin takes pity on Oscar and allows the ball to drop to the sand. The ball drops a distance h of 2.0 meters from the highest point it reaches. Calculate the gravitational potential energy lost by the ball as it drops. So EP equals mass times gravity times height. We know the mass from up the top is 0.064 kgs, which is 64 divided by 1,000. We know that gravity is 10, and we now know the height is 2 meters. So we grab out a calculator and we type in 0.064 times 10 times 2, and we get 1.28 joules, which we could say is 1.3 joules because 2.0 is only two significant figures if we wanted to get technical. Okay, II, calculate the maximum speed of the ball could have when it hits the sand. So we've got EK equals a half mv squared, and if we assume that all of the gravitational potential energy is converted into kinetic, then we can say that this equals the 1.28 joules, and so we can do some algebra. So we know that a half and m are being multiplied by v, and so the opposite of doing that is to divide. So I'm going to get v squared equals 1.28 divided by a half times the mass, which we know is 0.064. And I need to square root that answer, so I can chuck that into my calculator. 1.28 divided by, I'm going to put brackets because I want it to be the whole bottom line, 1 ABC2, which is a half, and I'm going to times that by 0.064, and I'm going to go equals. Now that's 40, so v squared equals 40, and so the velocity itself is going to be the square root of 40. So my calculator, I go shift little button to get the square root, and then I go shift answer, and I get an answer of 6.3 meters per second, which is good. If I head over to III now, explain why the actual speed of the ball the instant before it hits the ground will be less than that calculated. Well, we said before that EK equals 1.28, and we said that was because EP equaled 1.28, and we said that those two numbers were the same because energy was conserved. That's probably not going to be true because some of the energy is going to be converted to heat and sound. So let's write that down here. So as the ball falls, some of the energy is going to be transferred, converted, whatever terminology you want to use, into heat and sound due to friction with the air. So what that means is that the kinetic energy at the bottom will be less than the 1.28 joules calculated above, meaning that the velocity will be less than the 6.3 meters per second calculated. Done. Finished the exam. Well done. Congratulations.